So according to our schedule, first, please, Jan Goetz. It is a pleasure to have Jan Goetz at our conference. We met several times at Otaniemi when we were working at the Aalto University, and now Jan Goetz is CEO of also startup, known enough already, very successful. And if I understand, Jan also will touch a bit their activity in developing quantum physics, which would be a pleasure to know. What are the latest news, please?
Hello, yeah, thank you very much for this nice introduction. Let me share my screen. Does this work? I hope everyone can see this. So yes, hello everyone. I'm currently sitting in Munich. So welcome from Munich to my talk. As mentioned, IQM is a startup roughly 1 year old. And what we do is we build quantum computers using the superconducting technology. Today, I want to use my time to first give you a brief introduction into the company, where we are coming from and what we are doing. Then in the second part of my talk, I want to tell you our understanding of how to approach quantum computing and then show some latest results. So yeah, as it already was mentioned now a couple of times, is that it's very important, I think, to have this interaction between the academic community and the entrepreneurial world in this current situation of quantum computing, because also our understanding is that we have to work here together in order to make the progress that is still needed when we want to build a quantum computer. And this is why for us as a company, it's also very important to be present at this event. I will therefore try also to have the talk rather technical. Nevertheless, I will also tell you a little bit about the business understanding that we have and have to have as a startup. So yes, IQM, just in very brief, to give you the basics. So IQM is a spin-out from Aalto University in Helsinki and the Technical Research Center, VTT. So this is where the technology comes from, and the founders have met. We are focusing on superconducting quantum technology, which is a well-established technologies these days. And we are funded mainly through venture capital. So we raised the funding round in July 2019, which was about 11.5 million euros. And in addition to this, we have several research grants going on to fund our research activities. Earlier this year, in March, we started actually also activities in Germany, in Munich, and I will tell you a little bit more about this. We have currently 55 employees in Finland and around 15 in Germany. Our staff is still highly academic, let's put it like this. So most of our people actually hold a PhD in quantum physics or are getting one at the moment. So actually we have also students who are doing their PhD work in our company. And so our people are still very focused on science, but now, of course, we are also bringing the business and the tech to this more industrial level. This is our goal. A little bit about the background of where we are coming from. So as some of you know, that in Helsinki, there's a very low tradition in doing the research in superconducting circuits. So already in the 60s, actually, the low temperature labs have been founded. And since then, the research is ongoing there in a very systematic manner. And this is, of course, very important for us to have this background and this infrastructure in cryogenics, as superconducting quantum computers are heavily relying on the fact that we are able to reach, for example, the low temperatures and the very well isolated environments. Another aspect that is very important for us is the nano and microfabrication. And there we are in this very lucky situation that we can use the Micronova clean room, which is operated by the State Research Center VTT. And we can use the equipment in there, which makes the production of the processors for us very efficient, also from a cost point of view. IQM has 4 founders, and you see here the 4 faces in the square pictures. Our chief scientist, Mikko Möttinen, who's also attending this conference, he was actually working together with Juha Vartiainen, our chief operating officers, already in 2001. So there's actually a very long connection between Mikko and Juha. And then Mikko founded the QCD labs in 2007, which are still running and which are kind of the basis for much of the technology that we are using. Kuan, our CTO, he was meeting Mikko for the first time in 2009 in Sydney, and then he came a little bit later also to Helsinki and was working many years there in Mikko's team, and then only had a short intermezzo still in Sydney before coming back and becoming one of the founders. I came to Finland in 2017 as a postdoc at Aalto University, and I was working there then 2 years in the group before becoming CEO of IQM. Then I mentioned this already in 2020, March, we were able to get also Professor Enrique Solano on board, which was a very big step for us as a company. Enrique was leading 2 quantum centers before, one in Bilbao in Spain and one in Shanghai. So he really brings a lot of expertise and knowledge, more from the theoretical and conceptual side into IQM. So at the moment we are operating from 2 places. On the top left you see actually a picture which is taken out of our office building. So they are close to Otaniemi still and at the research campus, close to where the clean room is, and also our labs are close by there. And then we have an office in Munich. So these are the 2 places where currently we have staff, and on the right hand side you see how our employee number has been growing over the last couple of months, and we are still growing, and we are still hiring highly talented people. What we are using, I already mentioned the Micronover clean room, which you see on the bottom left there, this building in the snowish scene, where we are fabricating our processors, and then we are bringing them into our lab facilities. On the bottom right, you see some pictures. There we have currently 3 cryostats, and on the top right, you see a rendering of our cryo hall. So in general, there we can fit in up to 10 fridges, and we are still also growing the number of fridges there. Just one slide about the business that we are aiming for, since we are a startup. As quantum computing still is a very early stage, we are really focusing on the pieces where we see most of the value in, which is the hardware. So our idea is that in the next few years, actually, there's a lot of value in having access to real machines, physical machines. And this is the idea of what we are doing, is that we are able to produce and deliver quantum computers and make them available. And the potential buyers that we see would be, for example, larger research centers, which don't yet have the expertise in building the devices themselves, but they want to have the access for their own research or for the education of the talents. But then also we think that more and more there will be supercomputing centers, probably in the beginning scientific supercomputing centers, and then maybe also later on commercial supercomputers interested in buying such machines. Just to give you some examples, currently there is a project going on in Finland where VTT is in the process of tendering for such a machine, and also in other places in Europe. Actually, we are discussing mostly with public entities, so governments, about purchasing quantum computers, near-term research-style quantum computers from us. So this is, in a nutshell, IQM, and the rest of the time I will talk a little bit about our approach to quantum computing, and then show you also some results. So starting from a very high level, of course, the motivation is to reach quantum advantage. And what you see here on the right-hand side is a map of possible fields or problems where quantum advantage could be reached. And in general, if you build computers, you have 2 approaches that you could follow. One is that you build a very general purpose universal machine that could then potentially solve in all of these fields or reach quantum advantage in all of these fields. So this is one side, but usually these universal computers, they require a large overhead on the hardware side. And the other approach that you could follow is a very streamlined application-specific approach, where you say we built a processor that is optimized just for one single problem and can run this over and over again. And usually these devices are very hardware efficient, but they lose, of course, the general purposeness. And for us, the trade-off is that currently we are highly limited by the hardware. So the quantum computers or the processors that you see out there with the 50 or 60 qubits that some of the people have, they're not yet powerful enough to solve these problems. So we really think the limitation is on the hardware side. And this is why we are focusing on these application-specific processors, which are then operating in a very hardware efficient way. So this is our idea. And then, of course, the question is, which problems do you focus on? And we are currently still evaluating this, mainly also with our team in Munich with Enrico Solano. But we see that probably these problems, they will come from the three fields that are highlighted here: chemistry, machine learning, and finance. So this is kind of our way of thinking. We are starting with these application-specific processors and making them more and more powerful until we have actually enough hardware resources that we can also develop a universal general purpose, probably error-corrected machine. But this is our way of going there. And we see that to go there, actually, you need to work still a lot on the scalability issues. And one problem, for example, is how to control millions of qubits or so. And this is something where already now we have some very early work on, for example, generating cryogenic signals. This is again in collaboration with QCD Labs at Alto and also VTT, where part of this technology has been developed. And then finally, on the processor side itself, this is where most of our IP is building quantum processors that operate faster or more precise than what we currently have. So this is where we are aiming for in the future. I just want to mention a little bit how we are seeing the development of these application-specific processors and what does it mean. What we are following here is a what we call co-design approach, which means that actually we are developing hand in hand the hardware and the software, because in our view, most of this inefficiencies of current algorithms and hardware comes from a very inefficient mapping between the algorithm and the hardware. And this is what we are focusing on. And what we are following here is a so-called digital analog approach. And this digital analog means that we are combining concepts from quantum computing that probably most of you know, which is, for example, NISQ concepts that you have single and 2 qubit gates. And we are combining these with so-called analog blocks, which could start in a very simplified form just by turning on multi-qubit interaction. So instead of only having single and 2 qubit gates, you could have multi-qubit gates turned on. So this would be the first step. But then the second step, for example, could be that you are working on optimized chip topology. So this is really how you are arranging the qubits on the chip, for example, breaking the structure of a square lattice and going into something more sophisticated. And then finally, the last step of this co-design is that you are bringing new components, for example, on the chip. And some of these components we have already in our labs. I will tell a little bit about them, like our quantum circuit refrigerator, but it could actually also be more new components that we are really placing on the hardware level on the chip. So on the chip technology that we are using on the hardware side, we have been focusing a lot in the past, still also at the university, on the problem of increasing the speed of the single operations. And this all boils down to the fact that we have to fight the rather short lifetime that you have, especially in superconducting quantum circuits, where the lifetimes are 100 microseconds or lower nowadays. One way is to just increase the lifetime. As we all know, this is rather tricky. So another way is also to decrease the duration of the gates and the readout and the read state. And this is what we have been focusing on a lot in the past. So we have actually, and I will tell you a little bit more detailed about this, we have actually developed concepts for the three main operations, for the reset and for the readout and for the gates. And I want to just very briefly walk you through the three of them and show you what we have been doing there already during the last year, and you will see a few slides about them. So this brings me to my results section. I will now show you some of the results that we have generated during the past year. So actually, when I tell all of this, we always have to keep in mind that our labs are now operational roughly for 1 year, since we had to set up everything from scratch when starting with IQM last summer. So a lot of time actually also went in up to setting up this system and setting up all the processes. On the experimental side, actually, we have divided our tasks into 4 teams that are working in parallel. We have a fabrication team that goes into the clean room and that is fabricating the processors and our test structures. So we are trying really to have a fast throughput of chips. So usually we try to cycle the fridges on a weekly base or so. Sometimes it works better, sometimes not so good. And what we have achieved here over the years is that we are now reaching coherence times on the order of 60 microseconds. These are record times. The average at the moment is maybe around 30-ish microseconds, and we are working on this. Also on increasing the quality factor of our readout resonators. This is something where we also working heavily on with VTT, the State Research Center in Finland, and also the uniformity. So how precisely are we actually hitting the specs? For example, specs like qubit frequency and coupling strength and all of this. We are constantly working on this and improving this. Then the chips are actually taken by the system integration team, which are taking care of the packaging and all the control, and they are then working on performing the actual experiments also in the lab. We are working heavily at the moment on improving our 2-qubit gates, but also we are now taking into operation a 5-qubit processor. We have some people working on the electronic side. So this is mainly generating in a very scalable way microwave signals. This becomes more and more important as the number of qubits scales up. So this is something where mainly electrical engineers are working on. And then in our software team, we are basically in a bottom-up building the software stack. So starting from the firmware actually for electronics, going up to a point where then we can interface with software partners. All right. So let me just show you a few examples of where we are experimentally. So one was the readout. So we have a concept of reading out in a faster way. Actually, this is something where we are still implementing it, because first, to get this so-called multi-channel readout implemented, we have to get single shot readout done with a high fidelity, and we are currently doing this again together with VTT's technology. They're actually providing the traveling wave parametric amplifiers for us, and we are currently tuning up the single shot readout fidelity. Currently we are still limited by the 2-pars that we get, but we are very optimistic that the numbers will increase in the future. We are now at the moment reaching fidelities of around 91% readout fidelity. On the reset side, we are using this component, which we called QCR. It's a quantum circuit refrigerator, which you see on the right, on the picture in the right. It's a structure that includes superconducting and normal conducting material, and what is happening there is single electron tunneling, and then through the single electron tunneling, actually it can be activated by microwave photons, and then these photons are leaving the circuits, and this is basically then how we reset from the excited state to a ground state, by taking out a photon from the qubit by triggering a single electron tunneling event. So this is the main idea behind it, and the experiments that we are running are roughly like you see here. We have on the left hand side you see a pulse scheme, where on the top this is the readout pulse applied to the readout resonator. And we are basically performing here a pi pulse experiment to the qubit. So we are bringing the qubit into the excited state with a drive pulse, and then we are applying a voltage pulse to this QCR, which triggers the photon absorption event. And then we are reading out with the resonator whether the qubit was in the 0 or in the 1 state. And if you make a real-time experiment, it looks something like this here. Where the blue line is when we just read out the qubit after applying a pi pulse without applying the QCR pulse, and then you just see the normal exponential decay of the qubit. And then the green line is when actually we are applying this reset pulse, and then you can see how the qubit decays very quickly from the excited state into the ground state. So this is where we are right now, and we are now performing more sophisticated experiments on actually characterizing the efficiency of this and also the efficient qubit temperatures and all of these numbers. Finally, for the gates, we are currently still tuning up and optimizing our 2-qubit gate using tunable couplers. So this is also work in progress. Currently, we are reaching at the moment gate times of around 50 nanoseconds, and we are now in the process of implementing state tomography to actually get also reliable numbers on the 2-qubit gate fidelities and being able to benchmark them in a more sophisticated way. The last example of what we are doing, just what I wanted to show you, is that, of course, to make all of this happening, there's a lot of engineering going on in the background. And this is not just one example I picked here, is that actually we have sorts of activities on the simulation side. And this means simulation on electromagnetic structures, as you see here in these pictures, but also simulations towards the dynamics of quantum systems. So modeling the loss mechanism and the dynamics, but also figuring out whether we could maybe derive better improved qubit types. So there's a lot of work going on in the background for designing new architectures, new chip designs, and maybe also new ways of realizing qubits. So for example, what you see here on the top right is just a simulation for magnetic flux control. So this is a simulation where you in the color code actually see the current density on the chip when we are applying flux pulses to tune the qubit frequencies up and down. And what you see in the bottom picture is just an high frequency electromagnetic simulation which we use to quantify the loss mechanisms in our structures, and this is the work that's going on in the background to support our experiments and also to design then future qubit structures. Just very briefly, I can tell you a little bit on what we are doing on the software side, since we are mainly a hardware company which is working bottom up. So we are really focusing on providing the software from the firmware level upwards. But of course, we are working heavily on integrating then our devices into a full stack. For example, we are working here together with Atos, the French company, which has some activities in quantum computing. And they're often offering also a programming framework and also some simulators, for example, this quantum learning machine, where we have one in Helsinki where we have access to. So this is, for example, something where we are working on. We're also working towards integration into Circ and other possibilities in the future. So this is our strategy there, trying to leverage the partnerships that we have already going on. So finally, just a short outlook of where we are going. We are now taking into operation a 5-qubit chip, which has also several improvements. For example, we are now including per cell filters into our readout structure, and this should allow us to make the readout more efficient and faster. We are also working on novel coupler designs to make the 2-qubit gates even faster and with higher fidelities. The first chips are now already in the fridge, and people are characterizing them. them, and we expect to have first results from them then later during this year. So this is kind of where we are at the moment, going, I think, with a pretty high pace. This is also due to the great team that we have working in the background. So I think we have really a high-class team, which is very motivated to make a global difference. And we are constantly hiring. So if you know someone or yourself are maybe interested in joining, just reach out to us, and we are happy to get in contact. So with this, I would like to thank you for your attention, and I'm happy to take any questions.
So please, questions, gentlemen. Has somebody questions? We still have a little bit time for discussion.
So the single shot measurements you can reach with the two pass from VTT, is that so, or you have
yes,
other?
these are the two pass from VTT that we use there.
Jan, can you? I'm interested to know. Did you say something about the architecture? Are you doing sort of the Google style, or let's say Valrav style with square lattice and basically tunable qubits, or are you using kind of the IBM style with driving via parametric couplers?
No, it's the first one. So we are using the tunable couplers and tunable qubits in between, because we think if we want to reach the short gate times and high on-off ratios, this is the way to go.
That's, I understand that. Yeah. And yes. Okay. Thanks for the moment.
More questions? Still a couple of minutes.
Another one, by the way. I can understand that it's extremely important to optimize all the ways you mentioned, measurement, reset, the whole thing, but you can only get that far with that. So are you making a really heavy effort into actually improving the coherence times? You need to go around 1 millisecond and beyond that fairly soon in order to really get off ground.
Yes, this is true. So, I mean, what we have done now is basically taking things into operation, since we only started 1 year ago. But actually, we are now setting up a dedicated group of people working, for example, in new materials and trying to find out what is a way to make a jump in the coherence. Because I think with the current combination niobium on silicon, we are already very far on what is possible. So I think we need to also make some disruptive changes there in terms of, trying to find better materials or a better way of shielding and all of this.
Okay, thank you.
Okay, so if there is no more questions, thank you very much, Jan. It was excellent presentation, very interesting. We are expecting new impressive results from your company, and we'll be happy to hear soon about the news.
Thank you. It was a pleasure.
So now we have to have Alexey Fedorov.
Hello, I'm here.
Another, well, it is not exactly startup, but it is Russian Quantum Center, also not, well, something intermediate between private company and what? Difficult to say. Anyway, it's Russian Quantum Center, very good center with a very good collection of strong research groups. And one of the bright researchers there, Alexey Fedorov, will present today.
Yes, thank you very much for this kind invitation, kind introduction. So may I start share my screen?
Yes, please.
Yes, so can you see my presentation?
Yes, we can.
Okay, sure. So thank you very much. Once again, my name is Alexey Fedorov and I'm presenting Russian Quantum Center. It is indeed very unusual form of development of science in Russia, since we are not a government organization, so we're a private research center in the field of quantum physics and quantum technologies. And most of the results that we are, obtaining, we are trying to commercialize and use in the cooperation with commercial companies. So in this sense, yes, we are kind of scientific startups, as one of our founders once explained. So today I would like to present our recent result. They are more like on the scientific side, which are developed to quantum state characterization with the use of machine learning. So that's, as we understand now, quite broadly defined activities around the idea of the use of classical machine learning in order to characterize quantum systems and use quantum information processing systems in order to enhance quantum machine learning, enhance classical machine learning algorithms. I will cover today one of the branches of these broadly defined research activities on quantum machine learning. So this work will present several results, and they obtained in a large collaboration. So in theory that several people like Yaroslav Harikov, who is now in JQI in Maryland, Evgeniy Kiktenko, who is one of the speakers of this conference. In the tomography project that I will present now, that's mostly collaboration with Alex Lvovsky group, who is between Russian Quantum Center and Oxford University. So before start, let me remind you about kind of recent news in Russian quantum technology landscape. Recently, Russian roadmap on quantum computing has been approved by the government. That means that a large research and development activity in the field of quantum computing is now started. There are some ambitious goals in this roadmap, and we hope that it will be successfully realized during next years. So my talk today will be about building sort of a bridge between quantum many-body physics and quantum technologies. So in a sense, we are trying to cover this topic. So on one hand, quantum many-body systems have a fundamental importance since they exhibit some non-trivial and exotic properties, like one can think of exotic and non-conventional superconductors, non-conventional transport properties, and new types of phase transitions. That all of these aspects are of fundamental importance in quantum many-body physics. And on the other hand, many-body quantum systems are useful in quantum technologies, so they can be used as a basis for quantum computing and simulation. They can be used for enhancing protocols in quantum communications and metrology. They're used in demonstration sort of supremacy, and etc. And now a lot of efforts are concentrated on the revealing properties of quantum many-body systems that can be of interest for quantum technologies. We would like to talk today about quite a specific challenge in theory of many-body quantum systems. It is classifications of various quantum phases of matter. Yes, classifying these phases of quantum many-body systems is crucial tasks for understanding various difficult problems. And this task is challenging since Hilbert space of many-body quantum systems is exponentially large. Most of numerical methods like Monte Carlo is not universally helpful for studying such systems, especially for fermions and highly entangled systems. And even in various well-known paradigmatic models of quantum many-body theory, like Hubbard models, there are still competing theories in various regimes, and there is a task of evaluations of these predictions for various regimes. And at the same time, there is an interesting progress in creating such many-body quantum systems in experiments with various types of physical platforms like ultra-cooled atoms, trapped ions, superconducting circuits, polaritrons, and many other systems. And today I would like to present two specific aspects of the use of machine learning for solving these problems. The one will be about revealing chaotic states in single particle and many-body quantum systems with the use of specific technique, which is known as learning by confusion. And the next part will be about enhancing of experimental quantum state tomography for continuous variables. So that will be basically about reconstructions of quantum states. They're quite different, but they're unified by the idea of the use of machine learning in order to enhance these processes. So before start, let me just kind of briefly remind you about classical machine learning, without deep explaining what it is, just maybe about some kind of physical analogy. So classical machine learning methods are based on the learning, which means the algorithms can progressively improve their performance with the data, yes, without being explicitly programmed, right? So instead of fixed all of the parameters of the program and make it very, very, strict, we have an ability to learn in the process of obtaining more and more data. And if, you are a physicist and you see on that, you maybe can think that it's very similar to using ansatz in solving many-body quantum problems. Let's say we choose a variational wave function and trying to approximate ground state as good as possible by progressive with progress on different types of regimes of quantum many-body system and etc. In this sense, there is an analogy between learning methods and ansatz techniques, and by now this this interface between the systems is also quite well explored. And one of the subjects that can be, learned with machine learning is actually quantum many-body physics systems. Why I already in parts mentioned, because they are complicated and understanding is important both for fundamental physics and applications. And there are a lot of works for recent years on applications of machine learning methods for classifying and finding different phases of matter. And the first example will be about revealing quantum chaos with machine learning. So let me first explain the technique that we would like to use, and the technique is based on the principle which is known as learning by confusion. The a priori knowledge about quantum systems, which is under our study, is only that there is a presence of two distinct phases in such systems, right? So we have a system, and there is a parameter lambda which controls transition of such systems between two different phases. And we would like to build a black box, basically, which will say us in which phase our quantum system is by now, in the phase 1 or it is in phase 2. And we would like to do this by the technique which is known by learning with confusion. Instead of this black box, we're trying to use a neural network. And what we're trying to do, we know that we have a critical parameter lambda in this case, and recognition is easy for deeply opposite regimes. For example, if lambda is equal to A, we know the system is phase 1 for sure with 100% probability. And the same for if lambda is equal to B, the system is the phase 2. And what we would like to do next, we would like to propose some critical value of lambda and learn our system and evaluate its performance. That calls, in a sense, of making confusion. We propose a critical point like lambda 1 and evaluate the performance of the neural networks at the condition that we learn it for such a lambda. And we learn and recognize and trying to achieve the best performance of such systems. In a sense, that means that if we choose lambda correctly, as much as close to the exact value, the performance of the neural network will be the best. That's our kind of like intuition behind this technique. And it has been proposed and quite well used. And what is basically outcome of this technique? It's what's called universal W shape. So universal W shape is basically the curvature of the performance of the neural networks, which correctly predicts, deeply opposite regimes between phase 1 and phase 2, and this maximum corresponds to transition between two regimes, between phase 1 and phase 2. And this technique has been applied to a variety of systems, like to finding Ising transitions as the Ising model and finding many-body localization. And you can see nice W shape for such systems. It's not every time exact, but that's characteristics performance of such neural network system. So we would like to use it for transitions of between regular and chaotic behavior. And we would like to start from very simple example from the chaotic states of billiard. Billiard is a quantum dynamical systems with a particle. Yes, and by changing the boundary of its geometry, we can change the transition between its regular behavior to chaotic. It's essentially single particle problems, no many-body physics at this point. And we have the, chaoticity parameter, which is controlled by geometrical shape. And there is a standard criteria for separation between regular and chaotic behavior. And this based on nearest neighbors energy level statistics, which unfortunately not every time accessible in an experiment. But as you can see here, if you have Poissonian distributions of E, that means that your system is in regular regime. If it is Wigner-Dyson distribution, that means that it's in chaotic regimes. And there is an idea to transform it as a criteria. So, and just a small connection between single particle task and many-body physics. Recently, a lot of attention has been paid to quantum scars, so specific trajectory, which appears in quantum billiard. And what is interesting that recently many-body analogs of quantum scars has been revealed in many-body quantum systems, and now there is a kind of bridge between these essentially single particle problems and many-body problems. In a sense, that resembles the idea of Anderson and many-body localization in a sense. So what we're trying to do, we basically learn this chaotic behavior for billiards with the use of convolutional neural network. So we use just probability distributions as an input data to our neural network and make this a recognition procedure. So that's the results for finding the critical point of the transition for different types of billiards. So for Sinai billiard, Bunimovich, and Pascal billiard. And what we observed here that actually only in very specific regime of the, on the very specific region of the parameter lambda, we have this, the probability to obtain this transition. So out of this region, so the recognition curvatures, which are presented as neurons, which are responsible for chaotic behavior, it's blue, and regular behavior there, they does not change with lambda. And we would like actually to make a confusion only with this highlighted region, whereas there is an uncertainty in neural network output. I will explain you later why it is interesting. So, and we already see can take a look that neural network captures some relevant physics. For example, for Bunimovich stadium, it's extremely challenging to find this transition point because it's extremely sensitive to variation of lambda, and we can see this sensitivity on our recognition curvatures. And as I already mentioned, there is a kind of the idea of making this confusion not in all the regions of lambda, but only in the region when there is some uncertainty in neural network outputs. This allows us to save computational time when we analyze the system. We make a confusion only in these highlighted transitions. So that's our results for billiards. As you can see, we recognize this universal W-shaped behavior, and we checked that the predictions of the neural network coincides with the transition point, which are given by the standard criteria of crossing between Wigner-Dyson and Poissonian distribution. There we present KL divergences. What we do next, we're trying to actually, generalize this technique for many-body quantum systems. And as example, we use spin chains, which is also a paradigmatic example of many-body systems. And we're also here interested in finding how transition between regular and integrable and chaotic regimes. So essentially, this type of neural network, this type of spin chain is Heisenberg chain, which is integrable, which can be solved by Beta ansatz, but by introducing either impurity of interaction, next nearest neighbors interaction, we can break integrability for some choosing of the parameter of lambda and obtain this criteria. And again, here we see this behavior. So we see uncertainty in the behavior of the neural network outputs, and trying to find our universal W shape here. And we successfully obtain that there is this universal W shape behavior for spin chains. So this technique is easily generalized for many-body quantum systems. And with the increase of the large of the system, the fact that we are trying to find this confusion regime only in the limited region plays an important role. just briefly say that we also try to use unsupervised learning for clusterization between this transition, and also successfully find this with variational autoencoder, these clusters of regular and chaotic behavior. So the next part of my talk will be about slightly different topic. It's about experimental machine learning quantum homodynamic tomography. That's our joint project with the group of Alexey Fedorov at the Russian Quantum Center. And here the task is quite different. So we need to characterize a quantum state basically, and we understand that single measurement would not work for the task. Repeated identical measurement also they give us only the projection on the one basis. And we need to use tomography, which means that we use many sets of measurement in various bases. But tomography becomes difficult with increase of the size of the systems. And that's partially because the numbers of the parameters grows exponentially. Tomography becomes difficult. Of course, sometimes there are some restrictions. So there are some ideas about what is the state of the systems. But in general case, it's very, very hard to characterize many-body quantum systems without any a priori knowledge about their states. An idea is again to come back to the use of neural network ansatz. That's a bit different approach in compared to what I presented before. The idea is to somehow encode, our tasks in the neural network. In this case, in the network type, which is called restricted Boltzmann machine. It's basically two-layer network with visible and hidden layer, and there is a connection, and they typically use for pattern recognition. So we just trying to adjust in our parameter in order to obtain recognized patterns. And recently, this idea, like a couple years ago, this idea has been used for solving many-body quantum problems and also for quantum state tomography, mainly for discrete variables, or like spin systems and things like that. What the idea behind that, we train basically two RBMs, one of the for amplitudes and another one for phases. And our RBM is trying to minimize log likelihood negativity related to a data set. That's how the original neural network quantum state tomography for discrete system works. And here we would like to adopt this for homodynamic tomography, which is basically the systems that can be used for characterizing quantum systems with continuous variables. So in this method, we measure actually quadratures, yes, of electromagnetic field. These measurements are phase sensitive. We change the phase of the local oscillator by piezo element and get measurement data as a set of pairs of quadratures. And one can think of reconstruction of Wigner function or density metric from this data. And the standard approach is to use log likelihood method and iteratively optimize the maximum log likelihood, as has been suggested by Alexey Fedorov. And the only problem that number of the parameters grows as a square of dimension of the Hilbert space. So it's quite intensive procedure from the viewpoint of the number of the parameters. And we think that using of the neural networks allows us to minimize the number of the parameters. So general idea is to use end units for represent Fock states, and we making a cutoff on some number of photons. And we think that reasonable numbers of hidden layers is order of the number of units, and we trying to train our RBM in the same manner as it has been done for discrete variables. But of course, there is some kind of technical tricks how to adopt this for continuous variables. And another important thing that we trying not only to generalize this technique for continuous variables, but also use mixed states, because typically in experiment we don't have pure states, and we use mixed states. And in order to adopt this procedure for recognition and characterization of mixed states, we use purification procedure. We simply think that our, density metric, let's say, is a trace on the environment of some wave functions, and we use it in order to recognize quantum states. That's, it's quite similar technically to a pure state. We need just two additional summations on the truncated Fock basis, but essentially the procedure is quite similar. And we applied this technique for various quantum systems. That's the result, for example, for this, in a sense, Kutrid state. Yes, we have three level systems with arbitrary parameters, And that's the recognitions of our data on recognition of our states on experimental data. In the left, that's RBM, restricted Boltzmann machine recognition, and right is a Max-Lick standard approach. So then we did the same for optical Schrödinger cats. And on both this example, we can see that, behavior is quite similar. Yes, so we have almost the same pictures. And, the clear answer is the clear questions, are there any kind of advantages of the use of machine learning instead of just standard approach with Max-Lick? And we're trying to find some specific answer on these questions. And the first, we recognize that RBMs learn the physics of quantum states, surprisingly, learn the physics of quantum states better. So if you can see on these pictures, on the photon statistics, Poissonian statistics for odd numbers of photons, but it is 0 for even photon numbers. And we can see that this perfectly recognized by RBM, but there are some deviations in Max-Lick recognition. So they quite significant non-zero statistics even for even photon numbers. And that's one of the advantages. At least on our data set and our states, we see that RBMs learn physics behavior of the system is better than Max-Lick. And another important ingredient is the fact that RBM significantly outperforms Max-Lick in the fidelity with respect to the number of the quadratures. So one can see on the smaller number of experimental data, the blue curvature, which corresponds to RBM, is high in fidelity rather than red one. And of course, that's what we expected. Because of more compact and more efficient coding of our states, we see the better, better recognitions and better representation. But what maybe the reason behind of this outperforming? It's quite surprising since RBM and Max-Lick optimize basically the same log function. Why RBM does this better rather than Max-Lick? And what we did cross-validation tests. And that's formulate our conjecture that the improved performance of RBMs is likely associated with lower overfitting. So overfitting is much less in the RBM approach because the number of the parameters for RBM is much less than for Max-Lick. So it's order of hundreds for RBM and order of thousands for Max-Lick. And we did this cross-validation test and obtained that indeed outperforming is maybe closely related or associated with lower overfitting. That's at least our conjecture about why RBM techniques for quantum tomography can be better than standard approach. On this, let me conclude and save some time for questions. Thank you very much for your attention.
Okay. So, thank you very much, Alexey. Does anybody has questions? Yes.
Well, I seem to be one of the questioners around here. I'm curious about this example you had on the W shape and the quantum, the billiards. In the solutions, obviously you don't have a quantum computer. And so did you use, let's say, quantum circuits to solve it, or did you solve it by sort of straightforward numerical simulations the ordinary way?
It's purely classical normal simulation. So there is no any quantum computing setups here. That's purely classical. And that's maybe one of the kind of the idea that with the increase of the size of the systems, on the one hand, it's very hard to expect that we can solve it, directly with classical computers. But we can think that maybe machine learning as a kind of heuristic approach to analyze at least helps us with some of the aspects of understanding of the behavior of complex many-body system, single, various
Okay,
quantum.
I'm sort of curious of this sort of quantum advantage aspect, because in principle you could solve these problems by simulating a quantum computer, then solving it, so to say, if you see what I mean. As I will be talking tomorrow about when you do quantum chemistry, actually trying to simulate a quantum computer might be much more work than actually solving the problem right away, straight for it. So I'm just curious about if you have any views on quantum advantage here.
Yes, but maybe that's in a sense related to more to the second part of my talk, because the part where we at least can try to touch this quantum advantage problem, it's related to how we would like to simulate quantum circuit. What will be our approach? And as it has been demonstrated for Google, they did it in a sort of straightforward way, but then IBM guys came up with the idea of using tensor networks in order to more compact simulations of quantum circuit. And I think that RBMs, or different types of neural network ansatz, can be also then employed for obtaining more compact representation of a quantum circuit for their further simulations on classical computers. In this sense, there is sort of a bridge to these quantum advantage problems. And I think that the approach that we use with these RBMs or different types of neural network ansatz can be promising for such a problem.
Thank you very much.
Thank you. Thank you. We're also actually doing at the Russian Quantum Center a bit quantum chemistry. So I would be curious to hear.
Okay, thanks. More questions? Anybody? Maybe I have a short question. You showed at the beginning something about coherent Ising machine.
Right.
Is that just mentioning of existing such things, or you do something in this direction?
Myself, I don't, but at the Russian Quantum Center, there is a big activity around this. Seems these coherent Ising machines, and story it's quite nice. So they, Alex Lvovsky, he is experimental quantum optician, and he worked a lot in this field. He found the original papers on coherent Ising machines and started to think maybe, he should try to do such an experiment at the Russian Quantum Center. But before, he asked his very smart PhD student to simulate this coherent Ising machine on a classical computer. And eventually, this very smart, bright student found that his computer simulation works better than really this coherent Ising machine in hardware. And that's one of the examples, what is called quantum-inspired classical algorithm. So they by simulating this coherent Ising machine, find a better way for optimizations for some problems, at least in discrete optimization. And now, by having this knowledge, as I understand, they trying to build coherent Ising machine, which will be better than its simulation. So that's how it is working now.
I see. Well, nice story indeed.
Yes, that's quite nice. So that's the story about smart PhD students and their, kind of non-trivial approach to solving the problems before making like this complex experiment with a lot of optical systems. Let's try to simulate it. And they gained a lot of interesting knowledge from this simulation. And that's one of the trends now why I put this here, because it's also in a sense related to this quantum advantage problem. When you're trying to establish this quantum advantage, you need to have very precise model in order to compare the time that you need to solve this problem classically or on the quantum way. So that's one of the examples.
Very good. Thank you very much. So it's, well, still 1 minute for short question if anybody has it. Otherwise, I invite Evgeniy Kiktenko, also from Russian Quantum Center, to give his talk. Please, Evgeniy.
Yep.
So the title will be Pseudostochastic Representation of Quantum Processes. So please.
Do you see my screen? Yes.
Yes.
Yeah. Okay. Dear colleagues, so hello everyone. First of all, I would like to thank the organizers for providing this opportunity. present these results. And today I will tell you the story about this pseudostochastic representation. So this is a kind of ongoing work. We have already 2 papers. One is already published, and one we hope will be published very soon. And there is a number of people who work on this project, and some of them are already on this conference. Okay, so you see this name, this title, this pseudostochastic representation, and first of all, I would like to tell what is actually this term means. And I start with some very basic things. So it's a kind of story from a classical probability theory. So let us consider just two random variables, x and y, which can take some values, and from the joint probability distribution, we can derive a standard Bayesian rule for these 2 variables. The probability for a random variable y, so it can be represented using the probabilities of random variable x using these conditional probabilities. Okay, and you see that we can rewrite this expression in a vector form. So if we put all the probabilities of the variable y and all the probabilities of the variable x in these vectors, so we see that these 2 vectors are related with a simple transformation which comes from this matrix S, which actually is a matrix of conditional probabilities. And this matrix of conditional probabilities, it's called stochastic matrix, and it has some very natural properties. First of all, the sum over all columns gives you unity. It corresponds just to normalization condition. So if you fix your conditions and you sum over all these y's, then you obtain, of course, unity. And the second natural property is that all the probabilities, all the conditional probabilities, they of course are non-negative in a classical case. So as usual. Next, let us go to the quantum field, and let us consider some Hilbert space, some d-dimensional Hilbert space, where some quantum states live. And let us assume that in this Hilbert space we can construct some set of elements. We can find some set of vectors. And the number of these vectors in this set is given by d squared, where remember d is the dimension of our space. And let us assume that these vectors satisfy the following expression. So the product of these projectors which are constructed on these vectors takes this form. And if we are able to find these vectors, then we can construct this POVM, what is called on these projectors, and this POVM is called symmetric information complete. So information complete because it consists of d squared elements, and this set can be used to decompose any operator. And symmetric, the term symmetrics comes from this symmetric relation of this scalar product. And it is known that really these SIG-POVM elements can be obtained for a number of different dimensions. The important is 2, of course, and some others. You see that if we have this PVM, we can actually represent any density matrix. Any density matrix of our state, we can represent it just as probabilities, okay, where these probabilities come from our PVM, and you see that these probabilities fully describe our quantum system, okay. And in the original form, we describe our state with the density matrix, and in this probability, we say representation, we describe it with this probability vector. And so this probability vector consists of real probabilities, which sums into unity. But however, they belongs to some subset of the full simplex of of different probabilities of the same dimension. And this set was called a qplex. It's kind of quantum simplex. Yes, it's a part of a simplex, of a full simplex. And so this is an example of this symmetric information complete POVM for the case of qubit. You see that these vectors corresponds to this tetrahedron, which is inside our block sphere. Okay, and you see that, for example, if we consider such probability representation, which corresponds to some deterministic variable, it does not belong to this qplex, to the possible set of quantum states. But for example, this one, which corresponds to a pure state, which this is an example of this state which belongs to the qplex. Okay, and actually, if we have, we fix our POVM, we actually can take some other arbitrary POVM. Here I take some E, which has arbitrary number of elements, this arbitrary M, and we can describe the probabilities of obtaining outcomes in this new POVM again with some matrix M, which can be easily obtained from our POVM and from our SIG POVM. And this matrix M appears to be what is called pseudostochastic. So pseudostochastics means that the first condition of our stochastic matrices remains. So all the elements in each column equal, the sum of all elements equals to 1. But however, in this quantum regime, we can obtain negative values as well. So they can be both positive and negative. Okay, and this is why these matrices, without this restriction on the positivity, they called pseudostochastic, or sometimes they called quasi-stochastic. Next, we can use this approach in order to study different dynamics equations. So, for example, we can take the simplest dynamical equation. It's for name an equation. If we have this equation, then we can for our Hamiltonian, which actually determine our evolution, we can construct this matrix, which here is denoted by bold H, is an analog of the Hamiltonian, and the resulting dynamic equation again takes this simple form. So we have this time derivative over our vector p, which in our case describes our quantum system, and this matrix H, it appears to be d squared times d squared matrix, which is real and it's antisymmetric. Okay. And actually, we can see that all the matrices which describe this kind of dynamics, they correspond to some linear subset inside the whole set of all antisymmetric matrices. And actually, we can write what is kind of a projector on a space of like good antisymmetric matrices, which corresponds to some quantum evolution. So it means that it corresponds to some Hamiltonians. Okay. Then we can consider the solution of this equation. So we know that in the standard representation, the standard formalism, the solution takes the following form, where U is a standard unitary operator, and in our SIG-POVM representation, U takes also quite natural form. This also this exponent of this matrix H, and it appears that this matrix U, it appears to be what is called pseudo-bistochastic. Bistochastic means that not only the columns of our matrix, the sum over all the columns gives us identity, but also all sums over each row also gives us unity. Okay. And it appears that this matrix preserves both L1 and L2 norm. So it's not unitary, but it's orthogonal matrix because all elements are equal to, all elements are real. And also it preserves L1 norm because we work with probability distributions. So the norm of our probability distribution should should remain to be the same. Okay. And so this is a general picture. So you see that we can consider a general space of all probability distribution, and inside this space there is what is called a cuplex, a space of these quantum probability distributions. And in the case of the full space, the set of maps which translates classical just standard probability distributions back to standard probability distributions should be described with stochastic matrices. We see that since the space of quantum state is smaller, that is strictly inside, we see it appears that the transforms which brings quantum probability distributions back to quantum probability distribution is larger. So you see that the stochastic maps are inside these pseudostochastics. And this is just a standard, this is just an example. So, for example, we can take a sigma z Hamiltonian, and this is a representation of this Hamiltonian in this picture. And so the solution, this unitary matrix in this probability form takes this form. So you see that really it's a real matrix, but you see that some of this matrix, some elements can be negative. Okay. And next, we can generalize this approach to, for example, to equation which describes some dissipative evolution. For example, we take this Garini-Kossakovsky-Sudarshan-Lindblad equation with this form of generator where all the operators are time independent, and we find that so actually we can reconstruct the generator, this generator of this evolution. And it appears that this matrix, that we have this condition on the elements of this matrix. So if we take sums over each column, it equals to 0. And we also can construct a kind of projector on a Markovian dissipator. So if one takes a matrix, d squared times d squared matrix, real matrix, we can find a closest matrix which corresponds to a matrix which describes this dissipative part of our evolution. And then we also can consider, let's say, general solution of a dynamic equation, which can be represented as a quantum channel. So in standard representation, we can describe our channel with cross operators. And in this probability representation, we can describe it with this matrices S, which can be again obtained from our cross operators. And these matrices, so they appear again to be pseudostochastic. So the dimension given by this relation, so again the sum over each column gives you 1. And for example, in the case of this GKSL equation, this pseudostochastic matrix has this form. Okay, then you see that this representation allows us to study the, let's say, like a quantum classical transition. So you see that if you have some pseudostochastic matrix, and in some regimes, this pseudostochastic matrix will obtain that all the elements of this pseudostochastic matrix appear to be non-negative. It actually means that we come to this classical regime where all our quantum dynamics can be simulatable just by a classical stochastic process, and we can use, for example, some Monte Carlo methods in order to simulate these dynamics. And here we formulate some theorem about let's say the conditions on our generator, if in the case where we have this master equation, and we formulate the conditions on this generator L in order to the solution, the resulting solution, to be represented only by stochastic matrices for all times t. And it appears that the necessary and efficient condition is that all non-diagonal elements of the generator should be greater than 0. And automatically from this theorem we obtain a corollary that for the case of our unitary evolution, it means that we have so our evolution is described with Hamiltonian, which is not equal to 0, so it's some non-trivial evolution, it appears that this evolution, so this pseudostochastic matrix, will always have negative elements for some t greater than 0. So you see that the unitary evolution is always quantum. So the only case where we can obtain classical-like evolution of quantum system is a case where we have some dissipation, we have some decoherence, and actually we obtain this quite expected corollary that the decoherence is what actually makes the quantum process to behave like a classical one. And so using this, so if we have this generator, actually we can, so in our work we introduce some quantitative measures of its quantumness. Actually it's described by the maximal negative element of this generator, maximal non-diagonal negative element, and we use some optimization over additional rotations. Okay. And also another thing we can try to do is to introduce some measure of non-Markovianity. So, for example, if you have some pseudostochastic matrix S, which corresponds to your evolution, you can consider the closest evolution which is obtained from some kind of Markovian generator. Okay. And so the distance between the actual evolution and some approximation which comes from Markovian evolution gives you a measure of your non-Markovianity. And it's interesting that its measure seems to be practical since it can be compared with just your reconstruction error of your whole matrix S, which you obtain in your experiment. And we tried to make some experiments using this IBM Q quantum superconductive quantum processor. And so we consider this s-qubit measurement. Actually, we find that it can be obtained from this circuit, where this state psi, some fixed state, it is shown here on this Bloch sphere. And so using one C0 and Hadamard gate, you see that actually these 2 bits of information, which are obtained in the projective measurements, actually they gives you the result of your s-qubit measurement. And then we make some kind of quantum process tomography. We consider some experiment where we use some single qubit gate U, which is given by this unitary matrix, or in our representation it's given by this matrix. So you see that these negative elements, and we reconstruct this pseudostochastic matrix. And we know that actually in this experiment we have 2 kinds of processes. So the first process is our unitary matrix, which is not actually unitary because of some decoherence, and then we have this s-qubit measurement, which is also non-ideal. Yes, because at least we have this C0, which also causes some decoherence, and we reconstructed this pseudostochastic matrices, which corresponds to this unitary operator and to this measurement. And so you see that so this is the results. So we obtained really that the reconstructed probabilities, we obtained this negative conditional probabilities. And and the second picture corresponds to our measurement. So in ideal case, it should be the identity matrix, but you see that in reality we have something different. And then we calculate our measurements of non-Markovianity and non-classicality for these processes, and we find that actually you see that the measures of non-Markovianity are quite low compared to our estimated error of our reconstruction. And so we can say that the process in this processor are quite Markovian. So Markovian approximation works very good for it. And the noises which appears in the measurement, it looks like classical one because this measure of quantumness is equal to 0. However, the non-classicality of unitary operator is quite big. So it's nice because it's actually the unitary operator. So it should be quantum. Okay. And next we consider some generalization of this SIG approach to MIC. MIC stands for minimal information complete. So the idea is quite similar. So we have this POVM, which consists of d-squared elements, but however we have no this constraint on the scalar product between the elements of our MIC POVM. And the example of this of how can we construct our MIC POVM, for example, for many qubit case, is that we can take a single qubit. We know the SIC POVM for our single qubit, and then we can make a MIC POVM of our already many qubit system just by considering tensor products of elements of this SIC POVM. So importantly, this new POVM, which is constructed from symmetric POVMs, is not symmetric, but nevertheless it's still information complete, and we can use in our representation. And the general picture remains the same. So we have the states which we describe usually with density matrices. In this representation, they are described with these probability vectors. Again, if we have these CPTP maps, these channels, in this new formalism, they are described with some pseudostochastic matrices. Again, if we have some measurement, which is described some general POVM, in this representation we have this pseudostochastic matrices, and it's important that this representation keeps the tensor product structure of let's say quantum mechanics. So you see that, for example, if we have that our state is a kind of tensor product of two states, then if we go to this probability representation, the picture remains the same. So again, we have this tensor product of our already probability vectors. Okay, and it is the same for channels and for measurements. Again, we can consider that the tensor products of channels and the tensor products of measurements. And we use this representation based on MIC-POVM to study some dissipative dynamics. So we consider this let's say Limblad equation for short, which corresponds to some unitary evolution for a single qubit, which corresponds to some let's say to some magnetic field. Okay. And with this angle theta between this magnetic field and the z-axis, then we have some kind of dissipation, which is described with this Limbladian term, and we consider three kinds of dissipation of this decoherence. It's depolarization, dephasing, and damping. Some standard channels usually considered in quantum information, and we started a difference between different representations in a sense that we studied which kind of strengths of decoherence is required in order to make this process to be a classical. So we describe the strengths of decoherence by this variable tau. It's just a characteristic time of decoherence. And we try to find a critical time, which is critical time at which our process it looks like a classical. And it appears that for SIC-POVM representations, this value is lower than for a general case of MIC-POVMs, which corresponds to the fact that if we go from SIC to MIC, it makes us easier to employ classical stochastic theory in order to describe our quantum dynamics. Okay, and then we consider the representation of quantum computation in this picture. So actually, it's quite simple. So we use our SIC-POVMs in each qubit space, and we construct our general MIC-POVM. And so you see that the initial state is represented by the tensor product of these probability vectors. Then we can use some gates in this new representation. And again, our readout measurement, which is sigma z measurement in quantum computation, again, it can be written with this pseudostochastic matrix. And so here are some pictures of single qubit channels, gates, Okay, the pictures, and this is some pictures of 2-qubit gates. This is their pseudostochastic matrices. You see that they have 16. This is matrix 16 by 16 because it's 2-qubit. Okay, and this is just a picture of a Grover algorithm in this picture. So you can observe how the probability vector evolves in each step of this algorithm, and finally you obtain this result, you desired outcome in the single step of the Grover inverse algorithm. Okay, here I come to conclusions. So this MIC or SIG-based representation allows us to think about quantum dynamics as some classical probability, as evolution of classical probability distribution. Okay, with under an action of some pseudostochastic maps. All the basic quantum dynamics equation can be easily written, and this representation allows us to observe this quantum to classical transition. And actually, if we go to MIC-POM based representation, it makes our representation of quantum channel to be easy, to be more like classical-like, to be more like a classical evolution. And finally, this representation can be used for studying quantum computation processes. And now we are thinking about employing these tools of tensor networks for this representation, and to study some possibilities of efficient maybe simulation of real devices with some decay. And of course, you can see some more details in this preprints. Okay, with this, I thank you for your attention. Thank you very much.
Thank you very much. Questions, please. Is there any questions? Okay, maybe I have a question. Can you please say a bit more how you use it, your approach for description of quantum computers operation, single qubit, 2-qubit gates? In what sense it is better than some other approaches? What is advantage? It is a little bit like you can do it like that too, but what is the advantage of this approach?
Okay, so it's a good question. So the most interesting question for me personally, for example, is the following. So you see that any quantum computational circuit is actually can be considered as this pseudostochastic map with these negative probabilities, which acts on a classical distribution. And so you see that the origin of this advantage, of the supremacy of the quantum computers, it somehow comes from these negative probability distributions. And what is personally interesting for me is to understand how this negativity in these conditional probabilities, how they allows us to obtain the profit from the quantum computation. So I hope that this picture will help us to understand this quantum basics of quantum computation better, or even help us to design new algorithms, because I think this intuition of these negative probabilities can be helpful, because it appears that this negative probabilities is the only difference between some classical randomized algorithms and these quantum algorithms in some sense.
Okay, thank you. So other questions? Does anybody have questions? If not, thank you very much again.
Thank you.
And the next speaker, Alexey Pakhomchik, please. He will talk about, well, essentially, work on the supremacy.
Hello.
In brief, and yes, please, Alexey. Start.
Hello. Can you see my screen?
Yes, we see.
Okay. I'm Alexey Pakhomchik, and I like to talk about quantum advantage using a Gilbert algorithm for linear system of equations. Recently, the Google collaboration demonstrated quantum advantage by solving a problem that was purposely devised to profoundly demonstrate the advantage over classical devices. The low-noise superconductor 53-qubit device has been programmed to execute random instruction defined by a random quantum circuit containing single and 2-qubit gates. Such a random unitary transformation was designed to mimic all possible quantum computation. However, the implementation of a specific transformation that can be adopted into the framework of the practical quantum algorithm remains an open challenge. So in our work, they choose inversion of the matrix, all the matrix as an algorithm which run on classical and quantum computers and compare performance. On quantum computers, we solve this problem using hybrid HHL algorithm for Hermitian matrix. One of the main advantages of the HHL algorithm is exponential compression of the data. Therefore, quantum computers could operate on only several several dozen of qubits to solve a large system of linear equations, a task for which a classical computer would run out of memory. HHL algorithm require 3 registers, 1 qubit for ancilla, m qubit for phase. M is a number that is responsible for the accuracy of phase value, and logarithm qubits in the 4th register. The n is the size of vector b. It's size of the original problem. They encode a given vector b in amplitude of the 4th registers, and after executing the algorithm, amplitudes of the 4th register will be vector x. The HHL algorithm consists of 3 parts: quantum phase estimation, or QPE, ancilla quantum encoding, or AQE, and inverse QPE. There are 2 complex things in implementing this algorithm. The first is decomposition control unitary transformation into single gates and C-nodes, and another building AQE for 3 and more qubits. So we decided to consider subclasses of Hermitian matrices, and we formulate the original problem, and the goal is to find inverse of logarithm U matrix, not just inverse of some matrix. And for its implementation, we choose 2 subclasses of unitary matrices. The first is TP1, which is tensor product of single qubit gates, and then another NTP, which is not the tensor product of single qubit gate, but both type of matrix have 2 fruitful properties. The first is all matrices have the fixed spectrum, and another property is that the square of it is almost the same as the identity matrix. This leads us to highly simplified HHL algorithm. As you can see, we just have 2 phase registers, and QPS step. In QPS step, they execute control unitary transformation only once. it's important because complex circuit require require a large amount of CNOS, and final fidelity decreases dramatically. So this simplification is important. After executing the circuit, we must to calculate fidelity. So we had two types for different circuits. In low-qubit case, after executing the circuit, we made a full tomograph of the final states and compared it with the classical solution. You can see this fidelity in the left side of the slide, but in large qubit case, we couldn't make tomography because it requires an exponential number of experiments. So we used the cross-intermediate matrix fidelity. You can see it on the right side of the slides. This allows us to estimate the algorithm fidelity with only one experiment and single z-projective measurement. It's clear what the introduced matrix shows average proximity of the obtained vector projection to the ideal solution rather than a chaotic state. Now let's discuss classical methods of solving this problem. The most obvious way is to find a direct solution, but the fastest method works no less than 2 to the power of 2n, regardless of matrix sparsity. So the only way to solve it classically is to simulate a quantum circuit. There are two efficient ways for simulation: is Schrödinger simulation and Schrödinger-Feynman. The first one works faster but uses more memory. Therefore, it can be used for simulation circuits with more than 48 qubits. But in our work, we run experiments on 20 qubit quantum computers, so the Schrödinger simulation works well in that case. Then we get results. We firstly compare the efficiency of the problem this size to power of 17 problem solution implemented on computer, and compare this significant supercomputers in history. In order to properly compare classical machine and classical device, we must take into account the final fidelities since the equal fidelity computation task linear this cross-interpreted matrix. And while the net calculation time of quantum devices this 400% fidelity doesn't exceed 1 millisecond. The equal fidelity classical solution would require 10 orders of magnitude higher time for the supercomputer from the 16th, 8 orders for devices from 70s, and 4 orders for computers from 90s. Such a dramatic increase in speed is experimental evidence that modern quantum computer surpass the classical computing industry then arrived in 20th century. Secondly, they estimate the size of linear system should be processed in order to show quantum supremacy compared to contemporary supercomputers. For the execution time of hybrid quantum solution, we consider modern superconducting devices focusing on Sycamore processor. We estimate runtime of equal fidelity simulation implemented on 100,000 core modern supercomputer base 3 petabyte of RAM, and the quantum computation runtime are shown in the slide. We expect what the shared quantum algorithm solves the problem is more than 44 qubit problem can surpass modern classical solution and indicates quantum supremacy. Thank you for attention. If you have any questions, I'll be glad to answer it.
Yeah, thank you, Alexey, for a very nice talk. So, yeah, if you have any questions, please.
I have a comment only that I looked at the movie Terminator a few months ago or some time ago, and there was this computer called Skynet. And I have estimated that in this paper of yours, you actually beat the Skynet computer. So the world is safe in this way. You should be happy. Do you know what I'm talking about?
No, I don't. I don't heard about this computer.
Please watch it's a movie. It's not a real computer. It's a movie called
Yeah.
Yeah, and they give some numbers there. If you watch the movie, they give some numbers, and you can estimate from this table, not this one, but the previous one, where this computer would be. And it's actually beaten by this IBM nowadays.
Yeah, that's really nice.
So congratulations, we are saved. You have saved the world.
Yeah, that would be a great title for the paper. Yeah, thank you. So, any other questions? Okay, so otherwise, yeah, so it was the last talk of the morning session. So now we have some time to go and grab lunch and maybe to ask each other about these talks in more detail. So as I said before, this room will be available for the whole time, so you can freely be here. And thank you all, and see you soon in 2 hours.